So the topic for this next video is relations and functions in set theory. So in the previous video we showed how we can use the Kuratowski construction of ordered pairs to define the familiar concept of the Cartesian product of two sets from naive set theory in our new fresh Zermelo-Fraenkel set theory. What we now want to do really is take the concept of a function, the well-known concept of a function from naive set theory, and show how we can construct or define the same thing in our new Zermelo-Fraenkel theory of sets. And just as previously, where we want to avoid at all cost having to define something new that is fundamental or atomic, or define new axioms, we want to do that again. We want to avoid having to define something new, fundamental, and we want to instead try to define/construct this in terms of the things that we've already defined, and we're going to be able to do that once again for functions. We'll then look at relations, which are a generalization of functions, and in particular we'll look at ordering relations and equivalence relations on a single set. So here is a picture of our intuitive understanding of what we want a function to be from naive set theory. So remember, a function, we think of it as a mapping from one set onto another set. So we have our set A and our set B here, and we've taken very simple examples. So the set A is the set containing 3 elements, 1, 2 and 3, and the set B is the set containing 2 elements, which are called alpha and beta. And we know that these are going to be perfectly credible sets in our new theory of set theory. But back in naive set theory, this is how we viewed a function. So a function f was a mapping where it took every element in the original set, which we called the domain, and mapped it onto a function in the second set, which we called the codomain. So here we've got 1 and 2 being mapped onto alpha, and we've got 3 being mapped onto beta, and we would write that f is mapping A onto B. So when we're trying to make something that mirrors this, that is, I don't know, isomorphic we could use to this, that is encoding the same information as this. That's the crucial thing. We want to break down what information is this idea holding over here, and then can we construct something in our new theory without defining any new atomic ideas that holds that same information? And the answer is yes. So let's look at what information this holds. Well, all the information is for every element of this set A, you want to pair it up with an element from the set B. Now, we can do that in terms of what we defined in the previous video. So we defined the Cartesian product in our new theory of sets. So A cross B, I've written it out here. So it's all of these ordered pairs. So we have the 2 ordered pairs where 1 is in the first position, so 1 paired with alpha and beta, then we have the ones for 2 and the ones for 3, so each of them has an ordered pair with alpha and beta. Now, I claim that if I take a subset of this, I can encode in that subset the same information that is in this function, because if I just take the ordered pair where 1 is matched with alpha, the ordered pair where 2 is matched with alpha, and the ordered pair where 3 is matched with beta, that is telling me, that is matching each of these elements of the set A with an element in the set B, and it's encoding then exactly the same information as this picture here. So here is that done. So I claim that this is how we can realize functions in our new theory of sets. We can realize them as subsets of the Cartesian product of the domain and the codomain. So here is this function encaptured in a subset. So we have the ordered pair 1 alpha, the ordered pair 2 alpha, and the ordered pair 3 beta. And what this is telling us is where each of the elements from the domain is being mapped onto. The element that's in the B position in the ordered pair is the element that's being mapped onto. So this actually encodes exactly the same information as this. So this then is how we define functions in this Zermelo-Fraenkel theory of sets. So we can still use the old notation, so we can write that f is a function from A to B, but what that formally means is that f is a subset of the Cartesian product of A with B, and that subset can't just be any old subset of the Cartesian product. Not any old subset of this is going to be relatable with a function. Indeed, in order to be able to think of a subset of the Cartesian product as having or as representing a function, or as having an associated function that you could imagine being made from it, it needs to obey the property that each of the x elements from set A can only appear once in this subset, i.e. you can only have one of their ordered pairs. So you can't, for instance, have one alpha and one beta in this subset here, because then where would you be mapping one onto? You can't have one being mapped onto alpha and beta. The basic definition of a function is that each element in the domain is being mapped onto just one element in the codomain. Now the elements in the codomain can have multiple elements coming onto them, but you can't have multiple arrows coming from a single element in the domain. So you can't have one alpha and one beta in here. So the way that you'd formally write that is that for all ordered pairs x, y1 that are in this subset F, and for all ordered pairs x, y2 in F, so if you find another ordered pair where x is in this position, so this is the same x, then you've been an idiot. They're the same ordered pair. Y1 must equal y2, so you cannot find another ordered pair with the same member from the domain in the first position. So subsets of the Cartesian product that obey that property, you can think of them as they have an associated function, or you could use them to construct a function, or there is a function that that subset is the formal representation of. Relations now. Well, relations are just a generalization of the concept that we've just gone over for functions. So a relation between two sets A and B, we'll call it R, is again going to be formally a subset of the Cartesian product of A with B, but this time this rule doesn't apply. A single element from the domain of the relation, and we use the same terms domain and codomain for relations, a single element from the domain of the relation can be related to multiple elements in the codomain, so one can be related to both alpha and beta in a relation, a more general relation. So functions are very specific examples of relation that have to obey this property, that each element in the domain is only related to a single element in the codomain rather than multiple. So just an example, this subset, and indeed any subset, can function as a relation in set theory. But this subset is an example. So we're using the same two sets, this set, and we've taken nearly all of the Cartesian products now. The only one that's missing here is 2 alpha. So what this means is that 1 is going to be related to alpha, 1 is going to be related to beta, 2 is going to be related to beta, 3 is going to be related to alpha, and 3 is going to be related to beta. And we can write this as so. So 1R alpha means you would read this as 1 is related to alpha under this relation, and this would be read as 1 is related to beta, and then this is actually read as 2 is not related to alpha. And we're now going to look at some important examples of relations, namely equivalence relations and ordering relations, and these are where both the domain and the codomain are the same set, and you're defining the relation therefore just on one set, and we'll have a look at how important these ideas are. So equivalence relations then. So equivalence relations are going to be defined on a single set, and we've got an example here, the set 1, 2, 3, 4, which we're calling X. And the whole idea of an equivalence relation is that it can be used, the information from it can be used to partition the set up into what we call equivalence classes. Now these are just going to be subsets of the original set. So here, if you like, is the set now partitioned up into subsets. So we've split it up into 2 separate subsets, the subset 1, 2 and the subset 3, 4. And the information in an equivalence relation can be used to do this. So as it's a relation, it's going to be a subset of the Cartesian product, and here is actually a written example of how you can encode the information needed to do this partition here. So you can see that we've got 8 ordered pairs here. We've got 1, 1, 1, 2, 2, 1, 2, 2. Remember what all of these mean. 1 is going to be related to 1, 2 is going to be related to 2, 2 is going to be related to 1, and 1 is going to be related to 2. This is the information that allows you to put 1 and 2 into an equivalence class, a subset together, because they're both related to one another. You can see that nowhere in here is 1 related to 3 or 3 related to 1. So 3 is not going to be in the same subset as 1 or 2, because 2, as you can see, is not related to 3 in any way. Instead, 3 is related to 3, good. 4 is related to 4, and 3 is related to 4, and 4 is related to 3. So those two are then going to be in a subset together with one another, and like so. So we'll now look at the general axioms that the equivalence relation is going to need to obey in order for you to be able to use it in this way to split a set up. So in the equivalence relation, you are telling us what elements you want to be in a equivalence class with each other. So x related to another element means that you want those two elements to be in an equivalence class together. So if you don't make x related to another element in the original set, that means you don't want them to be in the same equivalence class. So the first axiom that the equivalence relation needs to obey is what's called reflexivity, and that says that for all little x is an element of your set big X that you want to put the equivalence relation on, little x must be related to itself. So it's going to be in an equivalence class with itself. So it must be related to itself, and what that means is that the ordered pair xx must be in your relation, your subset of the Cartesian product. Second axiom is called symmetry, and this says that for all little x and little y in your set big X, if x is related to y, i.e. you want x to be in the same equivalence class as y, then y must be related to x, i.e. you want y to be in the same equivalence class as x. So this is called symmetry because it means that you want the two symmetrical ordered pairs to have to be in the relation. And you can see that R1 up here has obeyed both reflexivity and symmetry. So all of the ordered pairs with the same element in both positions are in here. And then if you have one with two different elements in the two different positions, such as 1, 2, so 1 is related to 2, then you've got the symmetrical one. 2 is also related to 1, and the same for here. 3 is related to 4, 4 is related to 3, and that's plain common sense. You want this to be well defined. If you want one element to be related to another element, i.e. to be in the same equivalence class, you obviously want it to work the other way around, that that other element is related to the initial element. So those first two properties are very simple, and you can see that it's going to be very easy to construct a subset R of the Cartesian product that's going to obey these two. The final one is a biggie. This is much more complicated, and this is the one that really ensures that what you're doing is going to be well defined and is going to be able to be used to partition the original set up. And it says that for all elements, little x, little y, and little z, that are elements of the original set that you're trying to put the equivalence relation on, if you have that x is related to y, i.e. you want x and y to be in the same equivalence class, and you have that y is related to z, i.e. you want y to be in the same equivalence class as z, then it must be the case that x is related to z, so x needs to be in the same equivalence class as z as well. That, hopefully, is common sense to you, but of course, to make this obey that is not so trivial. You have to be thinking about what you're doing. If you just picked a random subset, it's going to be quite difficult to make it obey this. And what it means in terms of ordered pairs is that if x, y, this ordered pair, and y, z, this ordered pair, are in R, these are these two, then the ordered pair x, z also has to be in R. So let's now think about how we can use these three axioms to partition up a set. I did just use the word axioms, for which I apologise. The word axiom in maths is actually quite a bad word because it has such a broad range of contexts where you can use it, and these different contexts are on very different levels. So these things that we're defining here, these are definitions, these are man-made definitions, they're defining properties. They're not on the same level, for instance, as the axioms of Zermelo-Fraenkel set theory that we've previously discussed in videos in this playlist. So it's a bad word, axiom, because there's so many different contexts and they're very different levels that we're using them at. And this, this is much lower down than those axioms of set theory that we were taking as foundational to the whole theory. So I apologise for using that complex word. We'll call these defining properties from now on. So let's think about this definition and why this works then now. So if we have our more general set x here, and we have an element little x within it, then to make the equivalence class that little x is going to be contained in, all we do is we take all the elements that little x is related to. Now we know little x is going to be related to itself, so itself is going to be in there, and then all these other little dots are meant to represent the other elements that it's related to in our relation R. And the reason these definitions make this well defined is that if you were to take any one of these other elements that's in this X equivalence class and you were to construct their equivalence class, you'd get the same answer. So if we took this one, for instance, let's say this element is little y, if we looked at all the elements that it's related to, you'd get the exact same answer because of transitivity. So because little y is related to x by antisymmetry, we know little x is related to y, but we know now that little y is related to x by antisymmetry. And we know that all these other elements are related to little x. So by transitivity, it then implies because y is related to x and x is related to all of these other ones, then y is going to be related to all of these other ones as well. So you'll get the exact same set. And the reason you can't get anything else when you take the equivalence class for y is because if y was related to something outside of here, by transitivity, x would also have to be related to that because x is related to y. And if y is related to that, then by transitivity, x would also have to be related to that. So that's why when you take any one of these other elements and generate their equivalence class, you'll get exactly the same thing, and that's how this relation is well defined and can be used to partition a set up like this. So then what you'll do is you'll go to the elements that are outside of here, and you can then construct their equivalence classes, and you'll end up partitioning the set up. So that's why these defining properties allow a relation that obeys them to be used to partition up a set, and that's why it's called an equivalence relation. Finally, let's just look at ordering relations. So again, this is a relation defined on a single set, so it's going to be a subset of the Cartesian product of a set with itself. And the information that this is going to be used to encode is going to be ordering information. So if we take an example, the set 1, 2, 3 is going to be our set X. And let's say we want to encode the information of an order on this set. So let's say this is the order we want to encode. So we want 2 to be the smallest element, 3 to be the middle element, and 1 to be the largest element. So we can do this using a relation simply because x is going to be related to y is going to mean that x is going to be less than or equal to y. Now the reason that you use less than or equal to rather than strictly less than is it makes it easier when you ask the question about is x related to x. If you use is less than or equal to, you can then say that x is going to be related to itself because it is less than or equal to itself. Indeed, it's equal to itself. And that just makes things tidier. You could define it as less than. You'd then not have all of the ordered pairs where you have the same element in both positions. However, it's convention that we do it this way. We define the relation as less than or equal to and include the ordered pairs with the same thing in both positions in our ordering relation. So let's look at this example and then we'll look at the general definition of an ordering relation. So to encode this information here, the subsets we're going to need are given here. So when we look at 2, 2 is going to be less than or equal to itself, it's going to be less than or equal to 3, and it's going to be less than or equal to 1. So you need all of the ordered pairs for 2 in our relation because it's related to all of them. So 2, 2, 2, 3, 2, 1. So all of these are going to be in this ordering relation. When we look at 3, 3 is not related to 2 because 3 is not less than or equal to 2. So 3, 2 is not going to be in this relation. 3 is related to 3 and 3 is related to 1 because it's less than 1 and it's equal to itself. So these two are going to be in the relation. And then finally 1 is not going to be related to 2 and it's not going to be related to 3 because it's bigger than them. So the only one it's going to be related to is itself, so 1 is there. So these are the ordered pairs that will go into this set to make this ordering relation, and this encodes this information here. So this set with this is an ordered set. So the properties a relation needs to obey in order for it to encode an order like this, i.e. in order for it to be an ordering relation, well, again, it's going to obey reflexivity, just like equivalence relations did. So for all x is an element of big X, x is going to be related to itself. Nice and simple. We have already seen that because indeed x is less than or equal to itself. This time, instead of obeying symmetry like equivalence relations, it instead obeys anti-symmetry. So if x and y are elements of big X and x is related to y, then y is not related to x. So the meaning of this is that if x is less than or equal to y and they're not the same element, we're taking x and y as distinct elements, then that means that x is less than the y, and therefore y is not going to be less than x. So if you have the ordered pair xy inside R, then the opposite symmetrical ordered pair yx is not going to be inside R. So that's very different from the equivalence relation. And then finally, it needs to again obey transitivity. So if x is related to y and y is related to z, then x needs to be related to z. And again, hopefully that's intuitively obvious. If x is less than or equal to y in your order and y is less than or equal to z, then x needs to be less than or equal to z. So now let's see how these three properties allow us to think of this as encoding an order on a set. So we have our general set X here now, and let's think of it as having an ordering relation on it. And we now want to understand how, if the ordering relation obeys these three properties, it's going to be well defined, and we can use the information in that ordering relation to put the elements in a pictorial order. So to start with, let's just take the element little x here, which is in big X, and we'll start just by putting that on our piece of paper, and then we're going to put all the other elements in position relative to little x. So then we take the element little y, next element along in this set, and we're going to ask where should it be on the picture. So quite simply, we're going to ask, well, is y related to x? Because if it is, then it needs to be less than x, it needs to be on this left-hand side, whereas if it's not, it needs to be on the right-hand side. And we know by antisymmetry that this is all going to be well defined, because if y is related to x, then x is not going to be related to y, whereas if y is not related to x, then x is going to be related to y. So remember, y being related to x means it needs to be on this left-hand side, so you definitely don't want x to be related to y, because that would want x to be less than or equal to y. So the antisymmetry is really important. If this weren't true, you'd have contradictions that wouldn't allow you to put things in an order. Now, so let's say, for the sake of the picture, that y is related to x, so it's less than x, so it's in the correct position here. If you then take the next element along z, you want to know, should it be here, should it be in between them, or should it be over here? So to do that again, what you're going to look at is, how is z related to x and how is z related to y? So let's say that z is actually related to y, so it's less than y, so it should be over here. So you want to put it here on the picture. This is why transitivity is really important, because what if you just let any old subset of the Cartesian product be used as an ordering relation, you could end up with the fact that x is related to z and z is not related to x, which would mean that x needs to be less than or equal to z, so z needs to be over here, which would obviously be absolute nonsense. It can't be over here and over here. But by transitivity, that can't happen, because we know that y is related to x, so y is less than or equal to x, and now we're saying z is related to y, so z is less than or equal to y. So by that, z has to be related to x, it has to be less than or equal to x. You can't suddenly get that x is less than or equal to z. So that's why transitivity is so important. It allows it to be well defined. So z would go here. So I hope that's convinced you. Keep thinking about this. This is slightly more complicated than equivalence relations, but this property again is so important to ensure that this is well defined. So we'll now end the video there. We have seen how functions can be defined in terms of the things that we already have defined in our set theory, and then we've looked at this generalization of the concept of a function to a relation, and then we've looked at important examples of set relations on a single set, namely the equivalence relation and ordering relations.